Good morning, afternoon, everyone. Welcome to another webinar on the basics of using Tecplot 360. This time we will cover how to use the Specify Equations dialog, sometimes referred to as the Data Alter tool in Tecplot 360. My name is Jared McGarry. I'm one of the account managers here at Tecplot, but I've also I started with Tecplot as part of our technical support team, so I have some familiarity using Tecplot 360 for some of the interesting work that our customers use Tecplot 360 for. I'll also be joined today by my colleague and our product manager, Scott Fowler, to help field some of the questions that do come up. So if you do have any questions during the demonstration, feel free to enter them into the question field in GoToWebinar. And if you have questions following this, don't hesitate to reach out to us at support@tecplot.com and we'll be happy to help you. So this will be a more brief demonstration followed by a longer Q&A session. But today for the agenda, I will cover how to use the Specify Equations dialog. I'll begin with how to reference variables in your data set and then the appropriate syntax to use to create the equations and what functions are available to you. I'll also show how to use some of the if conditions that are possible in the Specify Equations dialog. And then some other neat tricks that are useful, like using letter codes like the I and J values in addition to some others. And then also show how to reference different zones in your equation for more complex equations. And then we'll close with the Q&A for any questions that have come up. So with that, I will switch over to Tecplot 360 to give first a quick tour of the Specify Equations dialog itself so we know what we're working with. So if we go to Data, Alter, Specify Equations, we can bring up the tool here. And at the top, we have the equation entry field where we can enter the equation itself. Below this, to the left, we have the Dataset Info button to bring up the Dataset Information dialog as a reference for the zones and variables in our dataset and what we want to use in the equation. So the Specify Equations dialog allows us to define new variables or alter existing variables in our dataset. To the right of the Dataset Info button, we have the Save Equations and Load Equations button, which allows us to reuse equations over and over again for different data sets. Makes it a little bit easier than having to type it over and over again. It saves it as an EQN file that we can reuse. Below this and to the left, we have the zones to alter in our dataset, which pairs with the zone list in the Dataset Info dialog. This allows us to choose which zones we actually want the equation and the computation to occur in. So we can select multiple zones or single zones or just select all to reset it to default. To the right of this, we have the index ranges, which isn't used too often by many of our users, but it can be useful. This allows us to change, for a structured data set, change the indices that we want the computation to be calculated in. So, for example, if we had a data set where most of the values are in the k=1 plane, we could limit the computation to just the k=1 plane to save a little bit of time in the computation. And then if we want to reset this to the default, we can just press 0 and reset it to the 1 to max index for k. Below these, we have the variable data type options, which allows us to output in a different data type for the variable. This can be useful for saving a little bit of time and size in the output variable, which we'll use in one of the examples today. Below this, we have the variable location, which allows us to specify how we want the variable to be saved, whether we want it at the node or at the cell center, or if we leave it at auto, it'll default to the values of the variables used in the equation above. And then for reference for any of this, I recommend using the Help button to bring up the section in the Tecplot 360 Users Manual for this dialog. And part of this dialog includes the full syntax that needs to be used for the equation tool. In addition to that, it also includes the full function list. So a part of this is some of the function commands like sine, cosine, tangent, square root functions, using if conditions, different operators that can be used, and then the derivative functions, which we won't be using in the demonstration today, or can be useful in some of your computations. So I highly recommend using that. If you do have any questions, or you just want a good reference for what is possible with the Specify Equations tool. And actually, let me bring that up here so we can take a look. So let me pan down a bit. So first, it begins with just an overview of the dialog itself. And then we have the syntax possible. And then these are some of the letter codes that we can use and will be using in the demonstration today. So X, Y, Z, U, V, W, which you'll see shortly. Below this, we have all the operators that are possible for the functions available to you. the if conditions and the operators needed for that, and then the derivative functions, which, like I said, we won't get into in the demonstration today, but can be really useful. And for this first example, what I want to do for this is calculate a new variable that's the momentum magnitude. So actually, if I open up that dataset info dialog again, we can see we have these momentum UVW variables, but we don't have a momentum magnitude variable that we could use as a contour or for something else. So to make our lives a little bit easier, let's just calculate it from the existing variables that we have now. So what I can do is I can select this text box with 3 different options for calculating the momentum magnitude. So if I Control C and Control V, just to copy it into here, now we're set up to compute it. But let me walk through first what these different equations are. So what we're looking at here is the same equation. We're just referencing the variables differently. So it's a square root of the momentum UVW variables that already exist in our data set. So the first example, we have the square root command, one of the functions. And then within that, we have, let me Control Z that. Within that, we have the full name of the variable that we're referencing contained in these curly brackets. So this works perfectly fine, but it can be, or it can make for a very long equation due to the long variable name, like an example like this. So the second example that is the same, but we're just referencing it a little bit differently, is using this shorthand for the variable number. So we have V5, V6, and V7, which pairs with variable 5, 6, and 7 in our data set. And that way we don't need to type out the full variable name or use those curly braces to contain it. And then even easier, for a computation like this third option, we can also use this letter code shorthand, U, V, and W, to point to the actively assigned vector variables in our data set. So if we want to check to make sure what those vector variables are, let's go to plot, vector, and we can see here that the momentum UVW variables have been assigned as our UVW vector variables. So those are perfectly suitable for this computation. Make sure if these are a little different, you'll want to adjust this to make sure the computation does make sense if you are ever using these letter code shortcuts. And then for this computation, I'm really only interested in what is going on in the fluid volume because we don't have any values for our momentum variables along the wing surface. So to save a little bit of time, I can just change the zones to alter to just the fluid volume and hit compute. We'll see this data alteration successful, and we have 3 new variables added to our data set. And I can click through these, and they are the same, but to make even more sure of this, what we can do is just place a slice through the fluid volume and then change to one of those newly calculated momentum magnitude variables. So let's change this to mmag. Contour legend updates for this, but as I step through the remainder of these, you can see these are the same. We calculated the same value. It's just how we referenced the variables that changes in each case. All right, so that's the first example I wanted to cover today. Let's step over to this next example, which will show how to calculate a new variable to create more complex geometric shapes for visualization in our data set. So this example that we're looking at here is a converged data set. And let's say I am interested in what's happening at or around the spark plug here. But the first step for doing that is finding the appropriate position for the spark plug and then creating a more complex shape around it, like a cone, cylinder, sphere, which I've already have set up for this. So to make our lives a little bit easier for that, we can save the position of the spark plug, the XYZ coordinates, into our auxiliary data. So to do that, if we go to Data, Auxiliary Data, and if I navigate to the auxiliary data for the data set, we have this X0, Y0, and Z0 values that have already been set up beforehand. And the way you can do this is by selecting Add, choosing a name, and choosing a value for this. So what we did in this case is we probed near the spark plug to find the X, Y, Z values, saved it to the aux data, X, Y, and Z0 that we have here, and now we can use these values in our equation so we don't have to type out the full string of digits for the position itself. So to look at the equations themselves, let me once again open the specify equations dialog. And what I'll do is I'll Control C, Control V this, and let's remove this additional text here so we can look at these equations. So we have equations to define a cone, cylinder, and sphere using some of the functions available to us, arctangent, square root, and then what we're looking at here first is we're referencing the X variable in our data set. So the X X, Y, and Z axis variables that have been assigned in our data set. So that's another quick shortcut. Rather than having to type out or adding the curly braces around it or using v1 to reference x, we can just type x, and Tecplot will know that that's the axis variable you want to reference. And then from that, we're subtracting the aux data, x naught, that we had defined in the auxiliary data dialog there, and so on and so forth for our y and z values as well. So that's an easier way to reference the position rather than having to type out the entire value itself. All right, and then for this computation, we're also really only interested in what's happening at the grid. So to save a little bit of time, we'll change the zones to alter to just the grid, which is the volume zone, which is where the visualizations will actually occur. And with that, we will keep the remaining defaults, and I'll select Compute. Data alteration successful, and to check, let's go to this data set info dialog to make sure we have these cone, cylinder, and sphere variables. And if we compare our existing X, Y, Z variables with the newly calculated cone, cylinder, and sphere variables, you can see that the variable location is set to the node, even though I kept this as auto. It defaulted to at the node because of the variables we were referencing, X, Y, and Z, were already saved at the node, so the resulting variables are also going to be at the node in this case. The variable type changed to double, or defaulted to double. I could have changed it to a single if I wanted to, which would match the float of the X, Y, Z variables type, to save a little bit of time if I wanted as well, if I wanted to do that next time. All right, so now let's try to visualize these and take a look. So the best way to visualize these new shape variables is using isosurfaces, and I've already got this set up here with this layout. So I open up the isosurface details dialog. First isosurface group, I have this cone. If I toggle on isosurfaces, now I can see this cone shape, and I can adjust the position of it by changing the isosurface value of it, which is the value for this cone variable. And then we can do the same thing if we want to show the cylinder, adjust it to change the radius of the cylinder, and something similar for the sphere variable. So these can be a great way to create more complex visualizations for your data set to get a little bit more information from it that maybe the 2D slice tool doesn't necessarily offer for your data set. So this is a great way to do that using a combination of the specify equations tool and using the isosurface tool. For the next example, I'll show how to use if conditions in an equation. So something that's really useful about if conditions is they can be used in combination with value blanking. So value blanking on its own, if I go to plot blanking, value blanking, what value blanking allows us to do is based on given constraints to cut away or hide portions of the plot and data set. And the limitation with the value blanking that the if conditions can help with is that value blanking is an or condition. So as I add more constraints, it'll blank when x trace is equal to 0 or x is less than or equal to 0, etc., etc. Now, if I wanted to use an and condition, that's what we want to use the if condition expressions in the equation tool. For this example that I'm looking at here, actually, I'm using an if condition to define a new variable that's giving me a 0 or 1 output to make a more obvious visualization that we're looking at. So what I'm looking at here, let me open up the specify equations dialog to look at this. Control C and Control V that. So we're just looking at the equation, just to save a little bit of time. So what I'm calculating here is this new max stress variable. And I've set up an if condition where the von Mises stress, if it is above a specified value, in this case 600, I will assign this new max stress variable a value of 1 if it is above 600, and if it isn't, a value of 0. So the result is going to be just a 1 or 0, where the max stress, if it's exceeded, we're given it 1, and if it's below, does not exceed it, it's given a value of 0. So because of that, what we can do is to output this variable, we can change the data type to a bit because the output is just going to be a 1 or a 0. We don't need it any more complicated than that. And that way we can save a little bit of space and a little bit of time in the computation itself. And with that, let's hit compute so we can take a look at this. Data alteration successful. And to visualize that, what I can do is change from this existing von Mises stress contour. And let's change that to, I actually have a second contour group already set up for the max stress, and I've already set up a different color map for it. So it's just a 2-color color map used for it. And for that, what we can do is change the contour group used to the second contour group so we can see the max stress that we've calculated. So we can see here the regions of max stress, or it exceeds that von Mises stress of 600, we're given in red, and everything else where it does not exceed is given in blue. And we can turn on translucency to see a little bit better. And as we step through a time step, we can see throughout the animation the regions of max stress that occur on our part. So one thing to keep in mind when using if conditions is you can run into a divide by zero error if you have any zero values in a variable that you're referencing. You can't get around this within the user interface because both sides of the equation are evaluated and the divide by zero will occur and still cause the equation to fail. So one way to get around this is using the macro language. So you can add this ignore divide by zero equals yes command to your equation and then run a macro with that same equation to get around any issues if you do run into a divide by zero issue like that. For the next example I want to look at, I actually already have the full calculation already set up and the resulting frame. But what I want to demonstrate here is how to do a zone reference in your equation. And for this example, this is used to do a differencing calculation between two different zones or two different data sets. So what we're looking at here is these two simulations were done at the same Mach value of 0.8, but they have a different alpha or angle of attack value, one at 0 and one at 9. So let's say I'm interested in what the coefficient of pressure is between these two different data sets. So the way that I can do that is if I go to data, alter, specify equations again, and this is a pretty straightforward equation as well. And what I can do is define this new CP diff variable. I define it in those curly braces, and then I reference CP in those curly braces. And if I want to reference just for zone 1, I'd use these square brackets, and then I subtract from that the CP from zone 2 and put that in square brackets again. I want to calculate for both zones in this case, and I'll just keep the remaining defaults, and I'll select compute. And look at this data alteration successful, and I already set it up, but the variable doesn't change because the equation results in the same. But now we have this new variable, CP diff variable, showing the differences between the two previous zones and data sets. And we can use a different color map, like this diverging blue and red color map, to more clearly see the differences between the variables used. Using the zone reference for variables can be really useful when you're doing dataset to dataset comparisons or zone to zone comparisons. It can also be useful when you're doing a delta calculation for a transient dataset where you can reference the zone for the time step that you want to compare, the time steps you want to compare between. All right, and the last example I want to show today, I'll use the same dataset and I'll zoom in a little bit, and let's toggle on the mesh so we can see it a little more clearly. Let's toggle on the mesh. There we go. Let's use it for the center one. So what I want to do for this example is demonstrate how to use some other useful letter codes using the I and J letter codes. So I've shown how to use the X, Y, and Z and U, V, W letter codes to reference the axis variables and the vector variables assigned in our dataset. Another letter code we can use is to point to the node or element number in our dataset. So for this, what I want to do is I want to define a new node num. I'll call it node num I, and that's because all I need to do to compute this is point to I, which is the letter code that points to the node number in our data set for a unstructured data set. So for a structured data set, we would point to our I index, and for a unstructured, it points to our node number. And so while I'm outputting this, I want to make sure that the variable location is changed to the node because of that, and I'll select compute. We'll get this data alteration successful. And to confirm that this computation went off okay, what I can do is I can use this probe tool, and I can control and left click to snap to the nearest node. And we can see in this variable list that results, at the bottom we have this newly calculated node num I variable with a value of 6097. And if we go to the zone and cell info tab, we can see that matches the node number of 6097 paired here. So calculating it as an actual variable can be useful for debugging your grid, or just as a way to keep track of the indices or the node number in your data set without having to click back and forth between the probe tool. We can get a variable that actually represents it. So we can do something similar if we use the J letter code. So for a structured, that would point to the J index, but for an unstructured data set like this, that points to the element or cell number. So I can define a new variable that's element num J. And again, just set that equal to J. And for this, because it's pointing to the element or cell number, I want to make sure the variable location is output at the cell center. And I'll select compute, data alteration successful. And let me reset the probe. So let's say I probe at this cell over here. And while I'm still on the zone and cell info tab, we can see the element number has 12336. And if I go to the cell center values tab to see what the element num_j variable represents, that's paired with it as well, 12336. So again, using the I and J letter codes can be a great way to keep track of the node or element numbers in your dataset as a variable representation. All right, and that concludes the demonstration and content I wanted to cover today. So just in summary, using the specify equations dialog, make sure to use the curly braces when defining a new variable or referencing an existing variable in your data set. As a shortcut, you can use V1, V2 to point to the variable number if you don't want to type out the full variable name. You can also use UVW or X, Y, and Z to point to the vector or axis variables that are already assigned in your data set. And you can use the I and J letter codes like I just showed. And then for reference on all of this, click the help button to bring up the section in the Tecplot 360 user's manual for the dialog for reference on the dialog itself and a full breakdown of the syntax required for the equations. And with that, I will switch over to some of the questions that have come up. So let me take a look at those. Before I do that, I guess I will announce that we do have another one of these getting started type webinars coming up on Wednesday, September 23rd, starting at 10 a.m. Pacific time. This time we'll cover how to use the Python API for Tecplot 360 that we call PyTecplot. So if you want to register for that, go to our the support page on our website, and it should be really useful if you want to use Python to help automate your work in Tecplot 360. And with that, let's see if any questions have come up during the demonstration. And to help me with this, Scott Fowler will be helping to answer some of the questions that have come up.
Great, thanks, Jared. Yeah, great job on the presentation. There were some questions that came up when people registered, and a couple other questions as well. So, Jared, I'm going to Slack a couple of links to you since you're sharing your screen right now, because I think the links will help when answering the questions. So, one question is, can I compute a time average over an interval? And the answer to that is it's not directly available in the Tecplot 360 user interface, but we do have a very robust Python language available. And we have some scripts that are available on a public GitHub site that Jared is displaying here. So if you just search GitHub Tecplot, you'll find this, this location. So we have a time average script here. And this script actually uses another script behind the scenes that we call tpmath.py. And that has a phased average function available in it. And because this is GitHub, it's supported by our user community as well. So the phased average was actually one that was written by one of our users. So we thank that user for that. Another question came in about classifying the contour and generating contours based on categories, so not really specific to equations. And unfortunately, I don't have a whole lot more information from the user who asked this question, but the contour legend in Tecplot typically just shows numeric values, and sometimes you want to show values that are string-based. So say you have different material properties, you know, like sand or soil in a geo case, or in the case of you know, the converged data sets that we've been looking at, you have particles that may be in the fluid or have bounced or rebounded. You can use strings using our custom label set. And Jared, I've sent you a link in Slack as well on that if you want to share the screen on how to do a materials legend. Yeah, right here. So a little bit of Tecplot Kung Fu to be able to do this using our custom label sets and show strings on the legend, but a pretty nice capability there. So yeah, please use that link as a resource. Another person asks, can I do a while loop in specify equations? Well, in the user interface, the answer is no. We do have a robust, like I said, robust Python language and a robust scripting language. So that last, one of those last cases that Jared showed, doing the difference between the two zones with that blended wing body shape, if, say that were a time-dependent simulation, you could use our looping capability to compute that difference over time. So the Tecplot macro language does have a while loop capability, and then Python, of course, has quite a lot of logical operations and flow of control type operations that you could use in conjunction with equations. Let's see, a couple other questions have come in. Jared, one is about academic pricing. Since you're on the account management side, do you want to tackle how we do student licenses or academic licensing?
Yeah, so we offer a couple academic license options for those who are at a degree granting university or institution. You can email me at campus@tecplot.com and I can help with specifics, whether you want a license just for yourself or if you want a group license. We also offer site licenses with effectively unlimited seat counts if you have an entire department, college, or an entire campus that needs to use Tecplot. So yeah, feel free to reach out to me with any specific questions you may have about that, because we have a couple options that can be useful depending on your use case.
Okay. And then a couple more questions have just come in here. Can we get a PDF of the presentation to help remember the equations? So we don't have a PDF of this one, but we could certainly probably put together some slides for you. This is, of course, being recorded and will be posted a couple of 3 days after the webinar, so you can always use that as a resource. So I guess I would suggest look out for your email, and we'll have a recording of this available, and you can grab those equations there. And like Jared said, always click on the help button in the specify equations dialog that can give you a reference to some of the functions that are available. Can an equation reference data in a different frame? The answer is, I think, ostensibly no. So each frame can have an independent data set, or it can have a shared data set. So if you load data into a frame and then create a new frame and then just switch the plot type, your data will then be shared. But if you load data in one frame and then separately load it in another frame, those are completely separate from one another. So no, you cannot reference data in that other frame, unfortunately. It would be interesting to talk to you about your use case. So perhaps we can follow up with you after the webinar. If I want to calculate the difference between different zones that have different meshes, what's the workflow for that? So what Jared showed here with the blended wing body data set, those two data sets have the same mesh, or those two zones have the same mesh. If you have different meshes, what you're going to have to do is you're going to have to interpolate results onto a common mesh with the same number of points. And we do have, oh great, thank you, Jared, for bringing that up. So so no, there's no better workflow than what you had already suggested in that question. Okay, looks like someone's trying to use the element number j equals j, but getting just one, not element numbers. Not sure what you're doing wrong. Make sure that you do use the cell-centered location for the result, and if you're still having problems, reach out to our tech support staff. Jared, do you see any other questions here that you care to tackle?
I see a question about license roaming, so it's not specific to using the equation tool, about the I guess the number of days allowed for roaming. So if you can email us at support@tecplot.com with your license, we can check to see if there's a way we can help with improving the maximum roam period, or finding another solution for you.
Yeah, if I'm not mistaken, the default maximum roaming period is 90 days for doing a roaming license. And that is, like you indicated, Jared, I believe that is defined license by license. So yeah, your license, the whoever administers the license at your organization will have to work with our support staff to extend that that date. Okay, how can I extract a circular line over time and make a contour plot out of the results? Let's say temperature distribution on the line over time. Output should be a 2D contour plot with axes being time and angular position. Let's see, so I think I'd have to spend a little bit more time thinking about that one than we have right now, and having an example data set from you would certainly be helpful. I immediately jumped mentally into using a polyline, our polyline tool. You can approximate a circle using our polyline tool, but that's not going to result in a necessarily a 2D contour plot like you want to call it. I think some people may call it a Hofmahler plot, and we've done some work with that in using our Python API, but I'd very much like to follow up with you after the webinar. I'm fairly certain that we can do this, if not in the GUI, certainly with our Python API.
All right, I see another question here, Scott, that's saying, is there a quick way in alter equation to find the deviation from a node value? For example, let's say I want to find the difference of u from its value at x equals 1, y equals 1, z equals 1. How can we do that? Scott, if you have other ideas, I'd like to hear them, but I think this could be done using the auxiliary data, like I showed in the second example here, because if you were looking at the value at a specific node number, we could save it to aux data and subtract from that, or we could alternatively calculate a new variable that just at that ijk index value to create a new u naught variable or something similar, and then subtract u from that. Do you have any other ideas for how that could be accomplished?
Yeah, I think I would probably just probe at x equals 1, y equals 1, z equals 1, and discover the value of u at that location, and then just create a new variable, which would be, say, udiff, which is udiff equals u minus whatever that constant value is.
Right. Yeah, that's a good point too. So yeah, if we probe, we can copy the actual value for the variable in question if we wanted to. We could paste the whole string in there, or save it as aux data, like I showed in this example, and then subtract from that.
And then here's another question: faculty working at a university and special pricing. Again, like Jared said, we do have academic pricing. So if you are interested in academic pricing, please do email Jared. It was campus@tecplot.com, Jared.
That's correct. Yeah. So email us there, and we'll get you pointed in the right direction, or get you the correct license you need.
Yeah. Okay. Quite a lot of questions today. Again, Jared and I are still here for a few more minutes. So if you do have other questions that you want to ask, part of this webinar is just kind of an open question-answer session. So feel free to ask any questions, or if you even just want to provide us feedback on Tecplot usability and interact with me as a product manager and Jared as an account manager, feel free. There's another interesting one that came in. Is it possible to track and store the position of a point on an isosurface over time in Tecplot? How can I do that? Yeah, this is an interesting one. So an isosurface, if you have a transient solution, an isosurface is going to get recomputed at every time step. So if you're thinking like a specific node number and tracking that over time, that's going to be pretty unlikely, because the isosurface is actually going to get recomputed, and the topography of that isosurface may change at each time step. If you're thinking just an XYZ location, well, then you don't need an isosurface in that case. So I think the critical thing is Well, I think that we'd again have to follow up with you about your specific use case to see if we can come up with a good solution. You know, you might be able to create an isosurface at your first time step and extract that to a zone, and then perhaps duplicate it through time. So you have constant node numbering throughout time, and then you'd interpolate results to that. It's one possibility, but again, I think getting your data and working with our support staff, we should be able to help you out and achieve what you want. Jared, you want to take this new one? I know that you've written a script to help identify min-max locations.
Yeah, so this question is asking, can we use alter equation to find max min of a variable and its location? So with the specify equations tool, no. So there is there's one thing to point out, that there is a function to find max or min, but what that does in the specify equations tool is it will calculate the maximum or minimum between two supplied existing variables, but it doesn't give you the max value of one variable and the location of that. But there is a script for that, or a Python script that I created with the help of our Python team to help get around this. Let me see if I can find it. But that is also saved up on our GitHub. So I think it should be one of the ones further down here. Display max variable value. So this script, you can run it, and you supply the zone and the variable through Python, and then it will in Tecplot 360 point to the location of the maximum value on your plot, and then display it in a little text box above it as well. So not through the specify equations tool, but it is possible to do this through some of the Python tools we have up on GitHub.
Here's another question about polyline data point extraction. It says that there are two options available, and which one should be chosen. There are a couple of different options for extracting data in Tecplot along a line, and I suppose it really depends on your use case. So I actually don't have the user interface running in front of me, but I can see Jared's. We do have extract precise line, which allows you to enter two XYZ locations. So that will allow you to extract data across a perfectly straight line between those 2 points. We also have the extract points from polyline, I think it is. Jared, can you go back to the data extract menu? Yeah, polyline over time, and
there's also if we just select a polyline and right click, you can select extract points from there as well.
Right. So I guess it depends on your use case for which one should be chosen, but we do have some options there. Is there any plan in the future to duplicate a page like we do for a frame? You know, I've heard that request one or two other times, so we have no immediate plans as we don't have a lot of requesters for the capability yet. But you know, I think that we could probably put together a Tecplot macro or a Python script that would be able to mimic that behavior by looping over each individual frame on a page and copying it and pasting it to a new page. So I think that's something that we could come up with a custom solution for you if that's something that you do frequently. Yeah, so if I extract a line across the wall, do I get wall quantities? Yeah, so that's a good question. So if you have a data set that has, Jared, if you can go back to the internal combustion case. So you're on it right now. Great.
Okay.
In this case, we have both volume data, which represents the fluid, and we have boundary data, which represents the wall. So when you extract across the line that Jared has there, it's going to extract points from the first zone that Tecplot encounters. In this case, it's going to encounter the wall. If you want to make extra sure of that, you could go into zone style and you could say show selected only. So Jared, if you just just double click on the wall in the UI. So that'll be selected, and then right click and say show selected only. So this will guarantee that your extraction is going to be coming from that wall zone. Okay, well, we've hit our time, so it's time for us to end the webinar today. I want to thank Jared. Great job on the demonstration today. Thank you all the customers and users who are using Tecplot and supplying us these great questions, and keep us improving. So as a product manager, I really love getting your feedback. So please do email our support staff. A lot of those questions do end up coming directly to me, and we'll help you out. So stay safe out there.